So this is the device which was fabricated in the lab of Andrea Marello in Australia back more than 10 years ago, which actually made it possible to perform really unique experiment. As you see, these people have been working on Keynes' proposal for more than 10 years. So what they've done, they covered the silicon chip by protection layer, and then irradiated with the whole sample with high energy phosphorus ions. And in this dashed line, you see this, my mouse is not working at the moment. In this dashed rectangle, they had a small opening of about 90 times 90 nanometer. And according to the flux of phosphorus, they were expecting there to have about 3 phosphorus ions in the small area. In the rest of the circuit, there was no phosphorus ions implanted. And then on top of that, they formed a device which has here a source. This is a source. Now mouse is working. This is a drain. And this is the middle electrode. And these are the two gates which were used to basically control the barrier between the two, the grain and the source and drain. And at the bottom, you see the characteristic picture of the Coulomb blockade. So when the voltage which was applied here is increasing, now this is the voltage at the middle gate here, which was changing the potential, basically like a gate to the middle island. And this is a horizontal one. And the vertical axis is the top voltage, which was applied basically here to the source. Then, as a function of 2 voltages, there was the origins of no current. You see the current scale is above, so the current was either very small. This is white areas, and red stripes is where the current was arising. And you see these regular stripes basically show us that there are regions of Coulomb blockades separated by lines of current. And if you go from one white stripe across the red stripe to the next white stripe, then the number of electrons on the middle island, on the middle grain, is increasing by 1. So when you overcome the Coulomb blockade, there is a current, and then you go from the state of n electron, where n, of course, can be very large, to n plus 1 electron. And this energy which you need to overcome is simply the voltage which you apply multiplied by the electron charge. So you see very irregular stripes here, and then there are some also irregularities, some offsets, and this could be some parasitic traps or maybe phosphorus atoms catching electrons. Of course, there was not particular single phosphorus atoms. This was in a way kind of probabilistic preparation. So one of those phosphorus atoms was working, and the others maybe were catching electrons once in a while and producing a periodic response. So when the phosphorus ions were implanted, they of course sort of mechanically destroy the lattice. So they go deep under the surface to a distance of about 15 nanometers, which depends on the beam energy, acceleration beam, which accelerates phosphorus ions. And in order to restore the crystal order around the phosphorus ions to make the crystal lattice regular and remove the disorder, one has to use here the thermal annealing. So basically, after the implantation, before depositing the metallic electrodes and forming all this device, the sample was annealed at 1000 Kelvin in order to repair the implantation damage. Of course, this is all probabilistic, but by increasing the crystal to the temperature of the crystal, you make the atoms move, and then they eventually occupy the lowest energy states, which are associated with the periodic lattice. So basically, these strips which are observed here, this increases the currents, which are changed proportionally to the top voltage and the plug gate. They show that the single electron transistor works and can be used to manipulate small charges nearby. And then it turns out that they have seen small shift of the line of the blockade, as you see here around this blue arrow. And that's where they were doing the experiment shown in the next picture. So next picture that shows the energy level diagram for this device, which you again see in schematic form here on the left. So there is a source, there is a drain, and there is this central drain, which is called SET single electron transistor island. And on the left, you see electron states which are located at the phosphorus ion. So these electron states can be occupied or not occupied. Of course, there will be only a state for one electron, but this electron can be either spin up or spin down, depending on the, this is probabilistic. So, and this electron can come simply by tunneling from the small island into the phosphorus from the surface into the bulk. And then the two energy states, which are associated with the spin up and spin down state of electron, which is trapped on the phosphorus ion, are shown here on the left diagram as red and blue line. So these are the two energies of the two. Mu is the Fermi level, or if you want, electrochemical potential of electrons in the island. And clearly, if we have an electron here sitting in the island, and the green states are the electron levels in the island, then this electron can tunnel from the from the middle island to the left, and then can occupy one or the other state, depending on the spin of the electron. This could be one or the other state. And then one can measure, in principle, the state of this electron by applying a small voltage between the plug gate and the island, and basically by lifting the energy level such that the spin up state will be above the Fermi level in the grain, and the bottom spin down state will be below the Fermi level in the grain. In this case, the red state will tunnel back to the grain and will change the current in the transistor, while the state with the spin down will not tunnel, and this kind of increase of the current from the transistor can be used as a readout. So basically, this is shown in the diagram below. This is the gate which you apply. This is a pulse gate. Where short time pulses are applied. When the voltage is at such configuration as shown above, then there could be either pulse of current or no pulse of current. And if there is a pulse of current, then the phosphorus atom state was occupied with a spin up electron, and if there was a phosphorus the spin down state was occupied, there will be no current occurring in the measurement. So basically, first one needs to load the electron with unknown spin into the system, and then by applying an additional pulse gate, one can actually determine which spin state it was. And in the readout, the spin down state stays at phosphorus, and spin up state tunnel to the SET, which is followed by, of course, by tunneling for another electron with unknown spin back to the phosphorus. So the last thing, of course, can be done if we apply larger pulse amplitude, and in this case, the spins of either state will tunnel out to the grain, and there will be current pulse. And by using this technique, by using this pulse manipulation, the spin state on this individual phosphorus ion was measured directly, and they measured huge lifetime of this state. They measured about 30 seconds single spin state on the island. Of course, they didn't measure the T2 time in this experiment, but this, of course, requires more sophisticated manipulation. Now, this result is shown on this picture. I think just for the sake of telling you a little bit about other techniques, we'll go forward. But basically, if you look into this paper, which is a kind of seminal paper cited by many people, you could learn about this experiment where they were able really to detect this individual spin state on phosphorus ion. Now, very recently, same group in the year 2022 They have done an experiment with 2 trapped ions, and this really took them another 12 years to get to the stage. And they were able to demonstrate 2 qubit gate fidelities of almost 99%. This is a really remarkable achievement, which was really very required a lot of work. However, it still remains to be seen if this technology using spin states of donor phosphorus ions or atoms in the silicon lattice, if this could be still scalable. So basically, this technology is there. There are experiments which really demonstrate it works. So it can be scalable, at least theoretically, but you have seen how long time it took really to implement 2 qubit gates. And only recently has been reported this high fidelity 2 qubit gate using the system. It has an advantage because it uses the conventional nano fabrication technology. It has full electrical control, high coherence times. However, the requirement here is that you need to place the phosphorus ions with very high accuracy. So this can be done with maybe with a focused ion beam, but making this process not probabilistic but deterministic is really difficult. The other problem which exists in all the small nanoscale electric devices is that there are parasitic charge noise sources on any chip. So any semiconductor device, like a transistor or superconducting devices, small size, or mechanical devices, they suffer from parasitic electron traps on the surface of circuits. Most of these traps really occur on the surface and can be due to the residuals of the fabrication, like residuals of the resist. They can be due also to absorption of various gases from the atmosphere, like oxygen absorbed on the surface and so forth. And this parasitic noise, they really lead to small fluctuations of the fields around, and this in turn leads to dephasing. So one really has to use special pulse sequences, like, for example, the spin echo sequences, or maybe even high order speed refocusing pulses, in order to compensate for low frequency fluctuations. And of course, these spins are also subject to influence of other defects, and the role of these sources of the coherence in large surfaces still remains to be unknown. So I would say that currently this field is at the stage where superconducting field and ions field were maybe 15 years ago. So 2 qubit gates with superconductors were demonstrated around 2006, 2007. So here the whole thing was still in the rudimental phase, but now they all can also show high fidelity 2 qubit gates. Well, we'll see. So time goes and miracles become possible. Any questions to donors on silicon? All right, let's go on. Next example of impurities-based qubits are qubits in diamond. So these are the so-called NV centers, and they occur in diamonds as kind of generic defects which occur in the crystals. As you know, diamond is the hardest material in nature. It's all made of carbon. And carbon atoms are packed in a dense fashion that they are, each carbon atom has 4 neighbors. So this is really the hardest natural material. So the crystal structure is face-centered cubic structure, and there are 4, if you look into this order, of course, you need to kind of imagine that there are 4 atoms in the unit cell, and then you sort of multiply this unit cell according to the symmetry of the face-centered cubic lattice. Now, the defects which occur in diamond make the material, diamond as a material, not fully transparent, or at least give some color. And natural diamond, which is found in mines, can also have different colors. And this all depends on the type of impurities. So the impurities can be nitrogen, can be boron, can be other type of impurities. If you take the diamond and place it in the source of alpha radiation, the heavy nuclei of helium, then this actually diamond gets green color, for example. So all these colors are mostly not desired for high quality diamond, which is used for jewelry industry, but some of them actually are quite rare and therefore are valuable. For us, it's not so important. For us, it's important that the diamond has a really very large band gap, so it has a factor of 5 or more larger than semiconductor, so it's really very good isolator. And if there are states inside this gap of some impurities, the states can be manipulated by light. So one of the typical defects which occur in diamond is the so-called NV center. NV is abbreviation which stands for nitrogen vacancy center. So imagine that you irradiate diamond with some high energy particles. This could be, for example, nitrogen ions, or could be also something else. Or you could, for example, put the nitrogen, put the diamond piece into nuclear reactor and then add some nitrogen atmosphere, and then high energy particles will destroy some of the sites in diamond, and then the sites can be occupied by nitrogen atom. So imagine that you have a regular lattice from which you took away 2 neighboring carbon atoms. And then instead of placing back 2 atoms, you placed back only 1 atom, which is a nitrogen atom, which is slightly larger than carbon, and therefore the neighboring place near the nitrogen stays unoccupied. So there will be basically a vacancy situation. How to do it is, as I said, you could, for example, bring it into the nuclear reactor, and then you need to anneal, to heat it up to high temperature, and then all the defects will diffuse away. And then if you do it right in the appropriate temperature, then most typical defect which will stay will be actually in nitrogen, which will come in because you could do it in nitrogen atmosphere, and a vacancy, which will form kind of bound state to this nitrogen. So, and then the material has the lowest energy state when the 2 electrons are getting trapped and form a quasi-pair around this defect location. So there will be basically 1 electron localized at the nitrogen atom and 1 electron localized near the vacancy site. So we know a lot about this because these kind of defects were discovered more than 20 years ago or even more in spectroscopy. And then the theory of this kind of defects was actually coming out from calculations using the well-known model for condensed matter physics, the linear combination of atomic orbitals, and also using the group theory based on crystal symmetry associated with this kind of defects. And if you make many of those defects, of course, you can observe them by using, or you can detect them by using the electron spin resonance. In Russian, it's called electronic paramagnitный resonance, actually discovered in Kazan many years ago. And basically, these defects have particular signatures which can be then detected in experiment. And of course, for this, you need many, many defects. So now, unique property of this defect is that it has a very well known and understood level structure. So it has the property of having effective spin 1 system, not 1/2 spin 1, because you have 2 electrons, one on nitrogen, the other one on the vacancy. And this is a resulting kind of spin state, because altogether there are 6 electrons involved into this spin 1 state. And of course, discussing all these details is a separate lecture course, which I'm not going to give here. Actually, I'm not really a specialist there, but just to give you an idea that you have here the singlet and triplet states of this spin system, spin 1 system. And the triplet state with the lowest energy is the superposition state, which is shown here. This is the state which is called lowest energy state 3A. And this is the ground state which has no spin because it's superposition state, but the 2 excited states of the same group are separated by small energy by few microelectron volts. And these are the spin up and spin down states, which are shown here by 2 arrows up and 2 arrows down. Now, above that, there are also states which are separated by large energy, and these are the states which you could excite by optical transition. So if you send high energy photons, basically laser light, to the system, then you can excite also similar states, and there are transitions between those groups of states. I will talk about them on the next slide. Now, there is a little splitting between spin up and spin down states. The splitting occurs due to a so-called crystal field, which actually is due to the fact that the electron orbitals are slightly distorted by the crystal lattice. And therefore, there is a splitting also at 0 magnetic field. So even at 0 magnetic field, you have a splitting between those 2 spin states. And in addition, you can, of course, control the spin states by applying the external magnetic field by introducing the Zeeman splitting. So in a way, this system is very well controlled, and there are transitions here in this convenient frequency range, which is about, this is between the ground state and those excited state, which are slightly split. So these are in the range of 2.9 gigahertz. Of course, you can also modify these states by applying mechanical strain. You can apply electric field and so forth, but this I'm not discussing here at this point. Now, when you apply light, then optical transitions are allowed for the change of the spin number equal to 0, so for non-G spin numbers. And there is a strong fluorescence which comes out when we go from the excited states to the ground state, which occurs at 637 nanometer, which is in the red part of the rainbow, and the intensity depends on the spin state. So there are some intense transitions and less intense transitions. And then basically you can manipulate the qubit state by microwaves. For example, you can encode the qubit into the lowest energy state and one of the spin states, or if you want in between the 2 spin states and so forth. And then you can read out them by laser. For example, if you apply the laser pulse, which populates the high states, then you will see the fluorescence of the particular intensity for a given state. And also there are some long-living state, metastable state 1A, which is populated because of decay with the change of the spin number state. So the excitation of the system to the visible fluorescent state can be achieved by pumping with off-resonant lasers. So basically you pump with this very large energy, and then some small energy before you get to those states goes into the phonons and other excitations in the system. And then those states here are occupied, and then the fluorescence can be observed. Now, the qubit initialization can be done by spin polarization, basically by pumping this to high energy state and then corresponding relaxation. So you'll prepare some of the lower states here in a desired fashion. And then the technique of doing the measurements will be basically applying light pulses and microwave pulses to these spin states, to individual defects. Now, the question is, how would we observe these individual defects? And this is really a very beautiful part of this technology here. The NV center is a single photon source. and it can be detected by using the so-called confocal microscopy. So in this case, you focus the laser beam not only in 2 dimensions, but you also make the focus in 3 dimensions, basically by choosing the focusing at a particular distance from the surface of the crystal, and then changing this focal point along the beam propagation direction. And then the setup involves the green laser, which is high energy, which you use for pumping and initialization of the qubit. This is green laser here, which is coupled here via the beam splitter. Then there is another beam splitter, which splits the beam into 2 locations with photon counters. So this will be the counting the photons as clicks, and the signature of second photon source will be that basically once the photon comes from here, it can either go to the right or it can go to the bottom. So only one of those detectors will click. On the picture on the right, you see actually the defects which were implanted using the focused nitrogen ion beam, and then annealed, and then you see here that individual defects, they show fluorescent response. You can control this, of course, by microwaves, as I said, and also by magnetic field. I should mention that pioneers of this field were 2 physicists from Stuttgart. This is Jörg Wrachtrup and Fyodor Zhelezko, actually scientist who is now professor in Ulm, and his background is in actually he comes from Belarus, by his education, and has been working in Germany for many years. So basically, how can we see that this is a single photon source? We need to measure the autocorrelation function. So basically, if we have now these 2 detectors, and we measure the signal from those 2 detectors as a function of delay between the measurements, then once the photon comes from the single photon source, it will either make the upper detector click or the bottom detector click. They can never click at the same time. And that means that the autocorrelation function, which we'll measure, will be depending on the time delay between the clicks. And if the delay is 0, then there will be no correlation at all. Basically, this means that there will be always one detector clicking or the other. However, if the delay is longer than a particular time, which is associated with the propagation path and also the intensity of the source, then the function actually goes to 1, and there will be independent, basically, clicks of those detectors. So single photon source actually can be recognized if this autocorrelation function is square is actually smaller than 1/2. And this is really the real data from the paper of Fyodor Zhelezko back many years ago, showing that this is really a single photon source fluorescent from atomic scale defect. It's interesting that if you use optics to detect or to observe some small objects, of course, you are limited by upper limit of the microscope. You cannot really do it better than the wavelengths. But once you have a single photon source of sufficiently high intensity, then of course this single photon source, while its size actually is an angstrom size, will nevertheless allow you to observe these individual defects, and you can recognize them as single photon source by measuring this autocorrelation function. That's really kind of beautiful technique showing the individual atomic systems emitting light. Now, this is really a big field where the most applications are not in the field of quantum computing. Obviously, it's very difficult to put atoms, NV centers, nuclear vacancy centers, at desired locations and control the interaction between them. So I only mentioned this is a sort of part of modern quantum technology. It's mostly used for sensing. And clearly, since you can detect the emission of light optically, you can measure very precisely very local magnetic fields, because the splitting between the energy levels, this fine splitting between the spin states of an electron at the NV center will depend on the local magnetic field. And therefore, you could apply microwaves, scan microwave frequency, and then basically measure the optical response. This offers an opportunity, for example, of measuring very local magnetic fields for very tiny objects. So one can make, for example, nanodiamonds at the tip of the scanning tool, and then image local magnetic fields of very tiny, also biological objects. The resolution of this magnetic imaging is not as great as, for example, for squids and Hall center sensors and so forth, but the advantage is really having very high spatial resolution. So not the field sensitivity, but spatial resolution is really amazing. Now, back to quantum computing, one, of course, can use the spin resonance technique to manipulate the spins. One can name the states with zero spin and non-zero spin as the two states you want to manipulate. And this is what is usually done in electron paramagnetic resonance or electron spin resonance. So one can initialize the system by laser, then observe the occupation of the state by fluorescence. And if you apply microwave, and then you have this resonant laser being your kind of measurement tool, then when you're occupying the state 2, there will be no fluorescence, and if you occupy the state 1, there will be fluorescence. And this shows the line which is observed in the bulk ensemble of the NV centers, and this shows also the energy splitting depending on magnetic field, which shows the spin states associated with this kind of defect. So one can measure, of course, Rabi oscillations there and apply increase the intensity of the microwave field. You see this intensity of microwave field is increased, and then the Rabi frequency increases. So this low frequency is A and high frequency is B. So basically all do this standard manipulation, but what is magic about it really that you could do it even at room temperature. So if you go to low temperature, to a few Kelvin temperature or even below, then of course the coherence times improve, but still you can have very appreciable coherence of the order of few microseconds even at room temperature. So one doesn't really need sophisticated setup to decrease temperature, but rather use, of course, sophisticated enough to use those lasers, but operating fully at room temperature. And therefore, this was really a very attractive platform to think about quantum computing. Nevertheless, until now, it remains very difficult to scale the system up to make NV centers at wish at desired places and also make them interact. However, some of the computing techniques have been demonstrated there. This was done, for example, by using coupling of the NV center to neighboring spins. Now, let me say a few words about the decoherence of this type of quantum systems. Now, in natural carbon, there are also carbon-13 atoms, which are a few, but they are always present. And to make isotope-free diamond, one really has to remove this, and you can imagine how expensive it will be making this diamond consisting primarily of carbon-12, which will be spinless. Now, there are also other isotopes of nitrogen. This also has to be paid attention. So nitrogen-14 has to be removed to avoid unwanted interactions of the NV center spins with the environment. Now, if one make ultra-pure diamond, which can be synthesized from isotopically purified carbon, then the dephasing times increase at room temperature from a fraction of millisecond to several milliseconds. And if one really purifies more and more, of course, this time increases further to tens of milliseconds and more. And this already would allow millions of gate operations, because the gates can be applied very quickly over time of almost a nanosecond. simply because the system is very unharmonic and you could drive it very, very hard and make the Rabi flopping very, very quick. So the range at which these defects can interact without being distorted by impurities, of course, increases, but you need really to bring them close enough, and this people try to do by implanting, but nevertheless, having the separation of about a micron, which is feasible for implanting, still leaves quite small strengths of the interaction, which is still kind of unsolved problem until now. What was done in terms of quantum computing was a demonstration. This was already more than 10 years ago, done by the group of Jörg Rachtrup in Stuttgart, where they were lucky, basically having occasionally an NV center coupled to two carbon-13 nuclear spins. So basically they had 3-spin system. And by doing this, they were able to manipulate 2 of those spins in a fashion similar to a qubit. So they were able actually to make a 3-qubit entanglement in this experiment using the level structure shown below for 2 qubits. And they were able to form these Bell states, which is more exactly for 3 qubits, are called Greenberg, Horn, Zeilinger. So this is a GHS, GHZ states. Don't mix it with gigahertz, but treats exactly the same way. On the so-called W state, which is written here, they were able to generate those states with relatively high fidelity and demonstrate elementary manipulations of this quantum information. But really going beyond these 3-qubit experiments, at least to my knowledge, there have been no success so far, while the people are still working and trying to implement those states. So my summary about these impurity states in nitrogen is on this slide. So the advantage is that coherence times, even at room temperature, are appreciably long. It's very efficient and convenient to read out these states by fluorescence, manipulate them by microwaves prepared by laser pulses. However, to make the coherence really significant for doing the quantum computing, one need to remove unwanted isotopes, to remove unwanted impurity spins. At the same time, one can use this impurity spins as quantum memory, which is also an advantage, but still remains to be seen if it really works. Excuse me. Difficulties, as I said, is really to make multiple qubits and scale up. The coupling of the light between the qubits, of course, is a possibility, but as I mentioned, also when you go from laser beam in free space to the waveguide on chip, then efficient couplers are really still difficult to realize, and therefore it's difficult to couple this type of qubits to photonic waveguides. So it's still a lot of potential here. If you want to know more, there are many groups, including this group of David Ashalom, who is now actually not in California anymore, but in Chicago. This is still an old review, which is still relevant. Here you could learn more about this type of states. And in Russian Quantum Center, there is a group of Alexei Akimov actually working with this type of systems with NV centers. So if you're interested, of course, he can tell you much more about that. Any questions about NV centers? Are you guys there? Was it too easy or too distant from you? Have you heard of this already? Can somebody answer?
So yeah, for me it was too distant and maybe too strange and too unusual. So yeah, I need time to think about it.
Do we have anyone who heard before about NV centers? Okay, so then I'm happy because I was not intending to give a really in-depth introduction, and what you have got from me was really superficial thing just to introduce that. And I trust you will hear more about that when you talk about other quantum technologies in the following courses in your curriculum. All right, so this is the end of my slide series. Let me share with you another file. Meanwhile, you are welcome to ask questions if you have some.
А можно еще раз повторить, в чем разница между Т1 и Т2?
Да, конечно. Т1 – это время энергетической релаксации. Когда вы приготавливаете два состояния, одно из них имеет большую энергию, чем другое. Да? Ну, любые, в принципе, состояния почти всегда имеют разную энергию. Тогда существует процесс релаксации энергии, когда вы переходите из верхнего состояния в нижнее, излучая фотон в среду, в окружении. Вот это время Т1. А время Т2 – это время, когда вы приготовили суперпозицию этих двух состояний. Если 50 на 50, вы находитесь на сфере Блоха на экваторе. И дальше у вас релаксации, вообще говоря, как бы, предположим, что ее нет, но есть, у вас дрожат как бы уровни, у вас меняется расстояние между уровнями за счет случайных внешних полей, за счет воздействия окружения. И тогда у вас состояние системы, которая есть стрелка Блоха, вектор на блоховской сфере, начинает диффундировать по экватору. И это есть время Т2. То есть это время дефазировки. Время Т1 чаще всего важно для приготовления состояния и для считывания, а время Т2 для манипуляции квантовой информации. Мы об этом говорили в первой лекции.
Хорошо. Понятно.
Okay, so let's continue with other examples of solid-state quantum systems, which can be used for quantum information processing. Do you see the slide?
Yes.
Yeah.
Okay, thanks. Okay, so in this lecture, in this part, we are going to talk about semiconductor technology and maybe a few words about some exotic subjects, but mostly about the semiconductor technology. So I told you already about ions, atoms, photons, about defects in crystals, which can be used also to manipulate and process quantum information. But now something which is really more close to electronics, about spins and quantum dots. Quantum dots. When you read the term quantum dot, quantovая точка, then different people think of different things. So there are, for example, this type of devices which have a size of a few nanometers, a few tens of nanometers, a few hundreds of nanometers. This is a so-called self-assembled quantum dots, which grow from gas phase on the surface of a pristine semiconductor surface, and then they form naturally kind of box for electron states, and then electron quantization in a box leads to discrete energy states, which are then forming the eigenstates of the dot. Sometimes people call the quantum dot a piece of carbon nanotube, which is actually which can be controlled by gates. And for example, you could localize electrons in a small fraction of the nanotube and then operate it as a quantum dot as well. But most common are quantum dots, which are actually produced by electron beam lithography by lateral confinement. So you basically make a two-dimensional electron gas, and then you confine the electron gas in a particular area by using the metallic electrodes on the surface. And here there are many efforts which have been done around the world over the last 20 years or so to demonstrate quantum computing capability of this technique. So first we discussed the initial proposal, which was put forward more than 20 years ago by Loos and DiVincenzo. Then I will briefly discuss two types of heterostructures which are used to make quantum dots based on two-dimensional electron gas. I will explain to you the readout using quantum point contact and the spin manipulation with quantum dots, and then later on I think I have two slides about most recent achievements, what was done there. So imagine that you have a semiconductor, and as the first example we can take 3-5 semiconductor gallium arsenide. And you may already know from your electronics or from solid-state physics course, this is a kind of semiconductor which is being used in a variety of electronic devices. So as a matter of fact, these were structures which were most convenient to make a whole series of very beautiful experiments with low-dimensional systems, with two-dimensional electron systems, quantum Hall effect, and similar, and also the one-dimensional and even zero-dimensional systems. One-dimensional will be quantum wires, and zero-dimensionals will be quantum dots. And here, basically, you take the gallium arsenide as a semiconductor, which is basically a good isolator at low temperature, and then you dope the semiconductor such that the band structure will be banded near this doping layer, and then the Fermi level will be above the bottom of this very thin doping layer, so that there will be only few electrons entering a very thin layer, which is shown here in yellow. And then you cover this layer by so-called cup layer, based on the differently doped aluminum gallium arsenide, and then cover fully by cup with another gallium arsenide. And basically, by using the trick so that you make the electrons distance from your impurities, this would basically allow for them to move freely. People have managed to achieve very high mobility, and these high mobility devices are used also in transistors and so forth. So this is a very beautiful solid state systems to study low dimensional physics, low dimensional transport, and so forth. And the motion of electrons occurs in only 10 nanometer thick layer of electron gas, which is so thin that the electron states are quantized in the direction perpendicular to the substrate, in the vertical direction on this plot. And the reason why it's possible is that because the electron density in this electron gas is very low. And for low electron density, you can recall your knowledge of the Fermi gas. You would have relatively relatively low mass and relatively large Fermi wavelengths. So the wavelengths of electrons in these two-dimensional structures is typically 2 orders of magnitude larger than the Fermi wavelengths of electrons in the metal. So it can be as large as few nanometers or even a few tenths of nanometers. And thanks to that, due to the large electron wavelengths, it's delocalized, and therefore it doesn't really interact with impurities, can move freely and achieve very high mobility. So this is the principle of making the high mobility semiconductor heterostructures, which have been known for many, many years. I think all the physics of 80s and 90s of electron transport was done with that. And then you place on top metallic gates such that you could sort of push away electrons by Coulomb forces from the area below the gates. So by pushing away, you leave two-dimensional electron gas only in this location here. So they are pushed away from here and from there. So only here you will have electrons in two-dimensional electron gas. And then if you make this this little island very small from other directions in this two-dimensional topology. And then, of course, you have a quantum dot. So in a way, this is a solid-state version of an electron trap. And you use the advantage that the electron wavelengths, as I said, or the Broglie wavelengths of electrons is really, really large, so you could really operate them as waves here. And the quantum dots, for example, two quantum dot configuration is shown here. They could be a little area of the two-dimensional gas. This kind of green circle shows where the electron gas exists, and outside this area, the electron gas doesn't exist. And then there is a left dot and right dot. Now, these dots are so small that the states of electrons in the dot are quantized due to the spatial quantization. As I said, the wavelengths of these dots is large, and therefore the energy level separation between the individual states of electron in the box is also quite large. And that's why one can actually use these quantum dots as quantum states of electrons, which are spatially localized. It's kind of little island with electron, which has advantage of having large extension, which can be controlled by the relatively macroscopic of few tens of nanometer scale electrodes. And also the spin states can be manipulated by magnetic field. And the proposal of using quantum dots for a quantum computer came up a really long time ago from Daniel Loos and David DiVincenzo, where they actually were proposing to use spin states in quantum dots to carry quantum information. The problem is that quantum dots, of course, carry charge, but as I said already in relation to defects, the charge is not a good degree of freedom because there are many sources of the coherence for the charge states. So there are defects on the surface, there are charge traps, there is a charge noise, and all the charges get decoherent very, very quickly. However, if you encode information in the spin states, which can be controlled, for example, by Zeeman splitting, then those spin states being different in spin but identical in charge, they will not suffer at all from random Coulomb fields. And therefore, they can be manipulated by magnetic field, and the coupling between them can be varied by the split gates, which are often called as J gates. So in a way, it's similar to the Kane proposal, which came about the same time, same year. You remember Kane paper with this sketch was appearing in Nature in 1989, and same year in PhysRev A, this proposal appeared. However, here is much more, I would say, technically easy task because you don't need to implant spins of phosphorus, but you basically form them, the spin states, on the surface of two-dimensional electron gas. And this size here can be as large as, let's say, a few tenths of nanometers or even 100 nanometer. So, and then in Kane proposal, electrons were only mediating interaction with nuclei. Here, you don't need to mediate anything. You work directly with the spin states of electrons on the dots. So basically, it sounds simpler. And it turned out to be really somewhat simple. Nevertheless, it really was very hard and difficult way to implement all the required steps for demonstrating quantum computing potential with the structures. So initial proposal of Loos and DiVincenzo was considering using a wire as a source of magnetic field, and then magnetic field decays away from the wire such that there will be different magnetic field magnitudes seen by the most left dot and then other dots and so forth. So magnetic field was decaying, and therefore the Zeeman splitting was decreasing from left to right. And therefore one can choose individual resonance frequency for different dots, which are located at different distance from the current carrying wire. And then one can basically apply the AC electromagnetic field to manipulate the quantum states, spin states of the dots due to the Zeeman splitting. The technologies which are used nowadays, actually there are two. initial technology was coming from semiconductor field, where the gallium arsenide was showing the highest mobility. More recent experiments, they involve different types of heterostructures, which are called silicon germanium heterostructures. Both of them have the virgin crystal. In the left case, in the case of gallium arsenide, is gallium arsenide. On the right side is silicon germanium. And then you have some layers which are used to form a two-dimensional gas. This is the aluminum gallium arsenide and then doped layer with a cup for the left structure. And then there is a silicon germanium, and silicon cup layer for the right structure. Now, this technology was developed a bit later. I think now they also can show very, very high mobility, but there is a tremendous advantage of silicon germanium heterostructures relative to gallium arsenide heterostructures. And this is due to the spin states of the underlying structures. For gallium arsenide, the natural mixture of gallium and arsenide consists all of nuclear carrying of isotopes which have nuclear spins. And while mitigating the results of these spins of the matrix crystal is possible, but really it limits very significantly the spin coherence of the spin dots. You have some random noise of the spins around, of nuclear spins, and these nuclear spins, they act as the coherence bus, as a noise source for the electron spins of the dots. So you see all the gallium isotopes, which there are two actually, which are major labudins of gallium used in these gallium arsenide structures. They're both magnetic, and they cannot be spin carrying states, and they cannot be used as neutral medium. In contrast, silicon and germanium, they can be made of really isotope spin-free states, and the making isotopically purified silicon is a quite well-established technology in semiconductor field. And one can have technique to remove silicon-29 isotope to completely eliminate dephasing due to the nuclear spins. Therefore, this is much more promising technique using group 4 semiconductors rather than 3-5 semiconductors for this type of technique due to the role of nuclear spins. The fabrication of these heterostructures involves the molecular beam epitaxy, where one can actually, in very high vacuum, grows the crystalline perfect structure on the substrate, making atomic layer by layer deposition. And this requires very high vacuum, as I said, and very slow deposition rate. It requires also appropriate substrates to grow monocrystalline films. Now, this has to be done at high temperature because the high energy components which come here from crucibles on the right, from the fusion cells on the right, they come with a particular disorder, and then the self-annealing is achieved by growing the structure at high temperature. And the technique to control that is the so-called reflection high energy electron diffraction, RHEID, which is basically controlling the order of the structure while it grows. So one can actually observe layer by layer growth of the structure and monitor this, and then guarantee the highest perfection of the growth during the process. This is really very well established process, quite very expensive, of course, but really established in the world. And in semiconductor field, of course, there are always champion growers in different places where you could get the highest mobility two-dimensional electron gas structures. But that's something, of course, which I'm not going to discuss. It's like cooking, and there are Michelin star, 3-star cooks, and if you just come and start cooking without really having a talent and background, then of course you are not aiming to end up immediately in Michelin guidebook. So this is also kind of art, growing the structures, not just skill. The MBE machine looks like this, and it's sophisticated. It requires really a lot of time and effort to make it work. And usually people who grow structures, they just do this. They just not do anything else. And of course, there are also some growers in Russia. And this is like the field, even the field for itself. Anyway, suppose you have this heterostructure, you got this wafer with grown heterostructure in a good place with high mobility electron gas, then you need to make the quantum dot. To do this, you have to use the electron beam lithography. And I'm going to speak about this also when I discuss with you the superconducting qubits. But just to give you an introduction, the technique is shown here. Basically, you use the electron beam, which is illuminating, which is focused on a thin layer of polymer, which is called resist, which is deposited on heterostructure. So you put some liquid with this polymer, then you dry this in the oven, and then you put this in the electron microscope or e-beam lithography unit with electron beam, and then you draw a line with electron beam. And electrons, they modify the bonds in the polymeric material of the resist. And then once you put this material into the developer, then the area where the resist was irradiated is removed. And basically here you have a line which forms a kind of gap between two pieces of polymer, which can be as small as the width of your electron beam. And typically in electron lithography, lines of the order of, let's say, 20 nanometers are possible. Then you evaporate metal from top, and then you put everything in acetone, and you remove this resist and the resist on the other side, together with the metallic layer on top, and what you are left with will be very narrow metallic electrode. So this is really something standard for semiconductor technology when one works with these low-dimensional transport structures. So this is the way you could make very narrow electrodes of the size which will be, let's say, down to 20 nanometers or so. And then you make a structure of these gates, such as, for example, shown here. So these are your metallic electrodes. You draw them with electron beam, and that's where your metallic film is located. And then you also need to make a contact to this two-dimensional electron gas and also to the gates. So top structures are called gates, and the two-dimensional gas is at some distance below the surface, as I already explained. So in this case, you have to deposit some metallic pads here and then use some moderate heating to make the metal diffuse into the material of the two-dimensional electron gas and form an ohmic contact to the two-dimensional electron gas. And then basically you can connect your wires to the two-dimensional gas, and you connect your wires to the top gates. And that's basically standard procedure, for example, of making high mobility transistors or making structures for low temperature transport studies of low dimensional systems. And again, that's something which I already explained to you. So to measure the charge on a small island, you use here single electron transistor, something we discussed already today in quite some length. But now the structure is formed differently. So here the source and drain are big pieces of the two-dimensional electron gas on the left and on the right. And then this little island is a small area of the two-dimensional gas, which is isolated from the rest of the two-deck by these electrodes, so that electrons can tunnel from the source into the island, and then from the island into the drain. And then this gate basically contains controls the potential of the island. And basically this single quantum dot can be used as a single electron transistor in a similar fashion to metallic transistor, which I described to you in relation to measuring the silicon phosphorus qubits. So by playing with these voltages you apply to these electrodes and playing with the shape, one can actually form an arbitrary shape of the potential, which has a lot of possibilities here. And then again, just sort of rephrasing what I already told to you, what you could do, you could fill the electron states in the island by making them tunnel one by one. And if there's a electron quantization states in the island, so basically electron in the box has discrete energy states because its wavelength is sort of comparable with the size of the system, and it gets states in the box. If you want, you can quantize it as a rectangular box. You know it from quantum mechanics how to get the eigenstates for the quantum box. And then the electron can tunnel into the box from the source if a particular state is not occupied. Now, this is the Fermi level here. Or the field states. These are the field states in the dot, and then if you bring the first state above the Fermi level below the potential of the source, then the electron will tunnel from the source, and if there is a drain electrode, it will also tunnel to the drain. So in this situation, there will be a conductance such that conductance will occur if the source Fermi level is above the electron state level in the dot, but that one is above the Fermi level in the drain. So in this case, you have conductance, and you will have this peak in the current, as shown here, and you have Coulomb blockade if the state is below, since electron cannot tunnel in all the states in the drain electrode, they're all occupied. So you need to have some states above the Fermi level then. And again, once you further change the voltage of the gate, then you will see that this also states which is show tunneling will be blockaded. So in a way, this is really a device which has amazing charge sensitivity, can measure electron charges down to a fraction of a million. So 10 to minus 5, 10 to minus 6 charge sensitivity is quite achievable. And basically, a current of many electrons is reached only by the current of half electron charge, and that's why we actually can use this for these high sensitive charge devices. So this is the operation of the single electron transistor, and what you do basically, you apply the two voltages. You apply source drain voltage and you apply the gate voltage, and then you start from having no electrons on the dot. This will be this area and this area, and then if you cross this line in this diagram, then you have one electron in the dot. If you go further up, you will have 2 electrons in the dot, and so forth. But then if you go horizontally, then you could sort of lock the electron inside the dot and then do something. And basically all these regions are characterizing different number of electrons in the dot are characterized by these peaks of currents, which are due to the increase of the tunneling current when we have a situation that the dot state is exactly between source and drain, and some current is applied between source and drain. So this leads to observation of the so-called diamond structures. And here on the diagram of the diamonds, you see here, for example, if you zoom, this is the differential conductance, okay? The dark area is where the current appears, and the red area is where no current takes place. And you see there is a large area when there were no electrons in the dot. This is this whole space to the left and to the down direction of this plot. But if you zoom here in this rectangular, then you see states with in the double dot. This is a double dot because you have 2 of them. So here you have no electrons anywhere. So both dots are empty. Here you have 1 electron in the left dot and 0 electron in the right dot. Because you applied particular gate. Here you have 1 electron on the right dot and no electron on the left dot. Here you have electrons on both dots and so forth. Now the most interesting, of course, is this area here. In this area, you see that you have a small joint between 0, 1 and 1, 0 state. And that's where an electron can tunnel from left dot to the right dot and back. And if the electron remains coherent, it can actually form superposition state, like in the double well potential, And this can be manipulated as a qubit, just as an example, of course. So this type of states have been, of course, manipulated. But remember now, the charge states are not coherent. We need to come to be able to control spin states. And spin states can be generated by removing the degeneracy with applying magnetic field. So you apply magnetic field, and then spin up and spin down states have different energy. You have Zeeman splitting. And basically, if you control now the gate, you move the Fermi energy in the dot up and down. Then you could make it possible to tunnel from the spin down state and not have any occupation of the spin up state, for example. So depending on the separation between the two states, you can manipulate now with source and drain and gate, and basically distinguish different spin states. And this is, I'm not sure if I have a picture later on, but this basically will lead to the splitting. So all these lines now here will be split in two lines or two spin directions. And then one can select between different spin directions and manipulate between different spin states. Now, how to measure the electron states on the dot? And one of the possibilities is to use the so-called quantum point contact. So quantum point contact is basically a one-dimensional channel, a narrow channel in which only few electron states, quantum mechanical electron states are possible. So basically, you make, imagine that you have electron wave function. The electron is moving in the two-dimensional gas, and then you confine the quantum point contact into the area which is so small that the electron wavelengths gets quantized in the direction across the channel. So you have 1, 2, or 3 bands, or if sometimes people call quantized channels of the electron transport through the dot. Basically, if the dot is smaller than the electron wavelengths, the wave will not go through. So if you have the wave which is seeing a hole smaller than its wavelengths, it will not go there. But if you make the hole a bit larger, then there could be propagation of the wave if the hole is half wavelengths, or it is 2 half wavelengths, or it's 3 half wavelengths, and so forth. So basically, it's quantization of electron state to electron wave function in transverse direction to its propagation. And this is the quantum point contact, which has quantized resistance. This is beautiful work done in the 80s by Bart van Wies and the others. And the station is really, this really led to amazing progress with low-dimensional structures in the 80s and 90s. So one can use a quantum point contact, which is basically a narrow gap between two metallic electrodes. You can control the width of this channel by applying a voltage to this quantum point contact gate. And then electron wave, which will propagate from, for example, from source to drain, will be very sensitively influenced by the fact if there is an electron in the dot or there is no electron in the dot. So the electron present in the right dot will have larger electric field effect on the quantum point contact than the electron present on the left dot. And therefore, by looking into the change of the current in the quantum point contact, which is this device here, one can distinguish if the electron is on the left or electron is on the right. And this is the technique of the projecting the states of superposition states of electron, which is tunneling between the two dots, on the localized states in the individual dots. Once you measure with the quantum point contact, then you would be able to tell where the electron is. Of course, you could also imagine here doing very weak measurements, but this is, of course, a kind of separate subject, which we are not going to enter now. All right, so the quantum point contact is known to show its plateaus of conductance, and each conductance change conductance is the inverse resistance. So basically, the conductance quantum is 2 square of electron charge divided by Planck's constant, and this conductance quantum is actually can be measured in also in variety of low-dimensional transport experiments done in the 80s. These are really beautiful works. If you don't know them, really very instructive to have a look there. So you can have 1 electron channel in the quantum point contact, 2 electron channels, and so forth. And well, I wanted to show here that these channels really exist, and people have been able to scan the cantilever of atomic force microscope to measure the local electric input. Actually, if you influence one way or the other channels, there is a change in the current, and people were able to visualize these channels in the quantum point contact. It's not just magnetization as a secondary demonstration, but also direct indication of the presence of this channel, those low dimensional transport channels in this low dimensional structure. Now back to the qubits. So people will see then a small change in the current in the quantum point contact if the electron tunnels from left to right. That's what I told you. The charge sensitivity of this particular experiment was not terribly great, but was sufficient to detect the coherent oscillations of the electron. It was about 10 to -5 electron per square root of hertz. And skipping the details, I can only tell you that, well, basically, this was what was observed in this experiment back many years ago, that the electron going from spin up to spin down state was split by the Zeeman energy, and then by applying short pulses, people were able to measure not only spectroscopy but also Rabi oscillations of the electron in this double dot, and also to measure the spin relaxation time, which turned out to be quite appreciable of the range of milliseconds at low temperatures. And this shows the resonance spin control. When you increase the amplitude of the AC signal, these are Rabi oscillations. As you see, the frequency is changing here. So again, we talk here about Rabi floating between 2 states and then measuring the projection on the individual state of the dot. Now, they were mentioned that charge qubits are not really favorable because of the charge noise, but these experiments have been also done showing very, very limited coherence, only of the order of a nanosecond, which is really tiny compared to the millisecond observed for the spin states. And the origin of the coherence in quantum dots is primarily the environment, which consists, of course, of the lattice having the magnetic spins of the nuclei. It has also spin-orbit coupling due to the other degrees of freedom. It has also fluctuations of the external field and further factors of the coherence. So there is plenty of the coherence factors which occur there. Now, there was a remarkable experiment done a few years ago where people were able actually to demonstrate 2 qubit gates in silicon germanium quantum dots with a coherence of the order of microseconds. And more recently, there were 2 papers in Nature actually published back to back with the paper of Marello group, which I mentioned earlier today, where they were able to demonstrate 2 qubit fidelities of the order of 99.5%. You see these diamonds are really very clean, and I'm skipping here the detail, but you see the degree of sophistication of this experiment. These color things are metallic electrodes, and this is, I think this is a micron here. I mean, no, this probably is a 100 nanometer bar. And yeah, this is really very, very advanced experiments, requires a lot of nanofabrication, a lot of patience in tuning up the voltages and then finally operating this device. But nevertheless, it's doable. There are 2 papers, as I said, published back to back very recently, and there is a very, very nice news in Nature on the perspective of spin qubits and quantum dots. So I think my time is up. This is my summary. So the quantum dot technology is very, very promising. of course, because it used semiconductors, it used electric control, but really quite sophisticated because one needs to use a lot of electrodes to tune the whole structure into the working points. The dephasing times are not really that long. And one needs to scale to many qubits now, though for simple circuits of 2 qubits, very high fidelity gates have been already demonstrated, but this is something, again, which when compared with superconductors and ions is like 10 years back. All right, I think I will stop today, not talk at all about helium. This is really kind of a little detour. Thanks for your attention, and please ask questions if you have any. I would love to have questions.
У меня есть один вопрос.
Да?
Правда, это глупый, наверное. Я немножко не уловил, а вот что используется в случае квантовых точек в качестве кодирования состояний конкретно?
Значит, в квантовых точках существуют дискретные уровни энергии для электронов. Это вы, наверное, поняли, да?
Да.
Вот. И эти уровни энергии, они, значит, соответствуют, значит, на них можно воздействовать, значит, электрическими магнитными полями. Значит, если мы воздействуем электрическими полями, то у нас, соответственно, эти уровни энергии меняются очень сильно, и это как бы есть состояние зарядования, то есть charge qubit. А если мы теперь с вами приложили магнитное поле и расщепили одно и то же состояние зарядовое на 2 спиновых, так, то это состояние, оно иммунно по отношению к зарядовому шуму. То есть зарядовый шум будет одинаково действовать на эти 2 расщепленных спиновых состояния. Поэтому для вот высококогерентных квантовых точек используются вот эти дискретные уровни, но которые возникают которые возникают при одном и том же количестве электронов на квантовой точке, но с разным направлением спина, то есть spin up и spin down. Используется дискретное состояние, значит, электронов вот в этом маленьком объеме, которые соответствуют одному и тому же числу электронов, но при этом расщепление создается магнитным полем за счет Зеймановского эффекта.
Понял, спасибо большое.
Угу. Еще вопросы, пожалуйста. Хорошо, ребята, значит, мы тогда с вами расстаемся на 2 недели. Как я говорил, на следующей неделе я не смогу читать лекцию, потому что буду в самолете. Надеюсь, что все будет по плану и прилечу в Москву. Вот. И через 2 недели, надеюсь, вас увидеть воочию, вживую, в квантовом центре. Вот. В это же время, во вторник, в 10:30. Хорошо, спасибо за внимание. До встречи.